Good evening, students. Am I audible to you all?
Yes,
Yes,
sir.
sir.
Good.
Yes, audible, sir.
Okay, thank you. So today is the fifth day of your last paper, MCH-004 of Postgraduate Diploma in Analytical Chemistry program. And for today's session, I would like to welcome you all uh, on behalf of my side and also from regional IGNO Regional Center Bhubaneswar. And in the last 4 days or in the last 4 session, we have uh, we have gone through different electroanalytical methods. The basic part followed by the potentiometry, and under it we have discussed pH metry. Then we have conductometry. Then followed by electrogravimetry, and yesterday we have discussed voltammetry with polarography and amperometry also. And today you have and we also completed up to unit 8 of your paper, MCS 004, block 3 unit 8. And today we have the last unit of your block 3 unit 9, and it is all about the applications of these electroanalytical methods, like application of polarography, application of amperometric titration or amperometry, followed by application of voltammetry. This is all about unit 9. And in unit 10, we will have one very popular and a new version of electroanalytical method, and it is called thermogravimetric analysis. So as the word gravimetry is there, that means it is a determination by weight. So that's why this is known as gravimetry. And thermo means it is application of heat or temperature. So when uh, the temperature is applied to a particular sample or electrolyte sample, then what happens? The degradation or decomposition of that sample will occur, which is followed by some mass loss, which is uh, which is determined through TCA, that is thermogrammetry analysis. So let's we have the first part, that is unit 9 application part. Then in the latter part we will discuss the unit 10, that is thermogravimetric analysis. So I am sharing my screen with you. Is this visible, students?
Yes, sir, visible.
Okay, thank you. So this is a very I would say this is a very easy unit or very approachable unit to all of you, that it is the application part of polarography, amperometric titration with voltammetry. And uh, the content of this unit are what are the objective application of polarography, followed by amperometric titration application. Then under polarography experiment we have ascorbic acid in citrus fruit, then followed by vitamin C, that is ascorbic acid in citrus juice by the standard addition and calibration curve method, and determination of other traces and minor constituents, determination of lead and copper in carbon steel, determination of cadmium in unknown sample, determination of the nature of the ion in terms of half wave potential E half, okay, that is ID by 2, limiting current divided by 2, this is will be E half. Then application of voltammetry in under this we have the instrumentation part, followed by some practical methods, and at the end we have cyclic voltammetry application. So what are the objective of this unit? We will discuss the elements or compounds determined with the help of polarography in different type of samples like food stock, seawater, fuels, etc. Then we will discuss the polarographic analysis of some organic compounds. Then some example of the species determined with the help of amperometric titration for different titrations and electrodes. Followed by we will explain different polarography experiment using both calibration method and standard addition method. We have two methods in polarography experiment, that is calibration curve method. This is the calibration with respect to one standard sample, and the second part is your standard addition method. Then we have this other industrial importance determination for traces or minor constituents, and then at the end will be cyclic voltammetry application. Then the first one is the application of polarography. So as we have already discussed yesterday, in polarography the current is determined as a function of potential, and generally dropping mercury electrode, that is DME, is used as the reference electrode, which function is to maintain the constant potential of the instrument, that is DME. So most of the metal ions are reducible at DME because they will form amalgam. That if it is copper, then copper 2 plus change to copper 0, and it will be settled on mercury. So that becomes one amalgam. Like zinc also forms zinc mercury amalgam. And multi-component mixture can often be analyzed by selecting an appropriate supporting electrode. The supporting electrolyte, this is generally the salt, this is the salt bridge, generally potassium nitrate. So that the halfway potential of the two ions difference by minus 0.2 volt versus saturated calomel electrode, or by using complexing agent. This complexing agent is our EDTA, ethylene diamine tetraacetate ion, by taking the advantages of complexing ability of the metal ion. So this is the complexing ability, because after formation of the complex, the metal ion becomes more stable, as this will form a cyclic structure. So you have to understand that the cyclic geometries are relatively more stable than flat geometries. So that's why by forming the complex with the complexing agents, the metal ion becomes more stable. Based on this, polarography is used predominantly for the trace metal analysis of the alloy, or ultra pure metal, mineral or mineral metallurgy, environmental analysis like air, water, soil, and sea contaminants, then also analysis of foodstuffs, beverages, and body fluids, toxicology and clinical analysis. Then what are the reducible anions used here? That will be bromate, BrO3 minus, iodate, IO3 minus, dichromate, Cr2O7 2 minus, nitrate, NO2 minus. Can also be determined using well buffered solution. Buffer, what is a buffer solution? Which pH is not changed when small amount of water, acid, or alkali is added to it. This is known as the buffer solution. It is again of two types: acidic buffer and basic buffer. Then these are the elements can be determined using polarography method from the sample this. So like from foodstuffs, we may determine copper, lead, tin, and zinc. From high purity aluminium, gallium, zinc, cadmium, and nickel. From steel, that is carbon based steel, we will able to determine the trace metals like copper, lead, nickel, and cobalt. Then from beverages, that is beer or soft drinks, you will tin or lead. High purity salt transition metals. It may be 3D transition metal, 4D transition metal. Then petroleum fractions. We have free sulfur from fuel, antioxidants from milk or pharmaceuticals. This is riboflavin. Then fruit and vegetable, vitamin C, that is ascorbic acid. Then sea water and gases, we will able to determine the oxygen percentage or oxygen part in the gaseous or seawater level. It is also helpful in the biological analysis to determine the vitamins, alkaloids, hormones, terpenoid substances, and naturally occurring substances, coloring substances, analysis of drug and pharmaceutical preparation, or determination of pesticide, herbicide residues in foods, in the structural determination of many organic compounds. So, polarography experiment can be used for many things, or as this method is very much useful for the determination of trace metal like this copper, lead, tin, zinc in different samples. So, this is a very much useful tool for the determination of trace metal in a sample. Then polarographic analysis of organic compounds. So this technique is used in organic chemistry for qualitative as well as quantitative analysis. Most of the organic compounds are insoluble in pure aqueous medium because organic compounds are soluble in organic solvents. So that's why as a aqueous medium is an inorganic medium or inorganic solvent, so that's why it is insoluble and it forms amalgam with mercury, and therefore the solvent in which the organic compound and its electrode product is soluble is added to the supporting electrolyte. The solvents may be alcohol, ketone, dimethyl formamide, acetonitrile, ethylene diamine, or others. The commonly used supporting electrolyte which are easily mixed with organic solvents are various quaternary ammonium salt such as tertiary butyl ammonium iodide. Someone is unmuted. Nages. Okay. So we have some reducible organic functional groups, such as this is the ketone, that is C double bond O, aldehyde CHO, alkene C double bond C, alkyne triple bond C, and azomethane. We have C double bond C again. So this is the azomethane group, followed by nitrile, azo, azoxy, peroxy, and disulfide. So these are the functional groups which can be reducible, and we have also nitroso, hydroxylamine, nitrito, and nitrate. So this is wrongly written here. The O is not there, only NO2. Okay. So if oxygen is linked to the metal, it is known as nitrito. If nitrogen is bonded, then it is called nitrate. So it is wrong. The O is not here. Okay. So these are the reducible organic functional groups. So then we have, in addition, dibromide, aryl halides, alpha halogenated ketone, or aryl methane and ketone, polynuclear aromatic ring system, and heterocyclic double bond reduces are dropping mercury electron. There is this is disulfide or thiosulfate. Sorry, this is SH. That is mercaptones get oxidized at dropping mercury electrode and gives anodic current. So these are the applications of polarography. Then we have some organic groups analysis of non-polarographic active groups such as carbonyl. The reagents are Girard T and D, semicarbazide, hydroxylamine. Then what are the active group? The azomethane, carbazide, hydroxylamine, such as this. So we have two types of functional groups are there, which are polarigraphically active and polarigraphically inactive groups. Okay. Then we have what are the application of amperometric titration. So in amperometric, we used the Ilkovic equation, right? That is ID, that is diffusion current. And for complexometry, we can use EDTA. So what happened? Yesterday I already explained, when a zinc in a solution, zinc 2 plus ion in a solution is complex with EDTA, ethylene diamine tetraacetate ion, the number of zinc ion will gradually decrease. So that's why the diffusion current will also decrease. This is a fundamental principle of amperometric titration or polarographic titration. Then we have the diffusion current at an appropriate applied voltage is measured as a function of volume. It is correct, because in amperometric we have along one's amperometric titration, we have a y in y-axis, we have diffusion current ID, and in the x-axis we have the volume of titrant added. So this is function of volume. So the equivalence point will be the intersection point of the two lines. That is charge, right, that is a change in current with the volume of titrant added at the equivalence point. Then we have complexation reaction with EDTA. What will be the electrode? That is dropping mercury electrode, and this combination can be used for many metallic ions for determination. So in precipitation, we have generally some reagents are here, like dimethylic lioxine for nickel, lead nitrate for sulfate or molybdenate or fluoride, mercury 2 nitrate for iodine, silver nitrate for chloride, bromide, iodide, cyanide, or thiols. Thiols means SH, it is thiol. Then thorium 4 nitrate in DME, it is fluoride. Potassium dichromate in DME, it is lead and barium. So this is all about your precipitation reaction, where by adding the suitable reagent or titrant, the metal gets or the ion gets converted to a insoluble precipitate. And in oxidation reaction, we have iodine with the platinum rotating electrode for arsenic and sodium thios. This is sodium thionate. Then we have potassium bromate and KBr. That is KBrO3 with KBr. We have rotating platinum for these things, arsenic, antimony, and we have a dinitrogen hydride. Then addition, we have rotating platinum for alkene, substitution for rotating platinum as electrode for some phenol, aromatic amines, etc. Then what are the experimental or practical experiments in polarography? That is determination of the nature of the ion by half-wave potential. That is half-wave potential of thulium ion, Tl plus. Thulium ion. So what is the procedure? That is 10 ml of zero point 0.5 millimolar solution of thulium nitrate in supporting electrolyte zero point 0.1 molar potassium nitrate, and draw the polarigram. Determine the half-wave potential from a reduction wave of thulium plus and compare with the literature value. Also use E versus log I by ID minus I plot for accurate E half. So this will be the experimental part, and this will be the procedure that using thulium nitrate solution with zero point 0.1 molar potassium nitrate as supporting electrolyte, we may determine the E half, that is half-wave potential, using this equation. Then we have determination of amount of cadmium in unknown sample. What are the steps? Step is wave height or concentration plot calibration. So these are the steps. That is, prepare stock solution of cadmium by dissolving this gram of cadmium per liter. From this, take 1, 2.5, 5, and 10 milliliter into 100 milliliter volumetric flask and 50 milliliter of 2 molar KCl solution and 2.5 milliliter of 0.2% gelatin solution to each flask and dilute to the mark. So these are the experimental procedures. Just go through these. That is the preparation of the standard solution, how to prepare the solution and how to prepare the supporting electrolyte. And after preparation of the respective solutions, we may go for the polarograph, and by from the polarograph we are able to determine the E half. Then after determination of E half, then simultaneously the amount or concentration of cadmium in the solution can be determined. Here it is written, draw calibration curve. The curve of the polarograph can be plotted. The wave height of all four standard. These are the four standard. That is with cadmium 2 plus of 1 gram, then 0.04 gram. Then we have 50 milliliter of 2 molar KCl, 2.5 milliliter of 0.2% gelatin. So these are the four standard solution or ordinates and concentration as abscissa. From this concentration can be determined. The method of standard addition. Polarogram of unknown solution is first recorded with under I, and the second polarogram is recorded by adding a known amount of same ion. Then the second polarogram with a different concentration of cadmium with different concentration of your supporting electrolyte with gelatin solution. So determination lead and copper in carbon steel. So this is another experimental part, and from this part you will face one theory question for your examination. So in this application, we have to determine the percentage of lead and copper in a carbon steel using polarography. So for this, we have to use the sodium tartarate as supporting electrolyte, that is have zero potential. Then we have iron 3 has to reduce to iron 2 with hydrazinium chloride in hydrochloric acid. So these things you will just go through, and these are very much simple things. And here just remember the iron is changed to iron 3 to 3 plus to 2 plus. That means it is reduced, and by the from the polarograph, okay, we will able to determine the percentage or concentration of trace metal in the sample using half wave potential. Okay, so E half of minus 0.25 volt versus saturated calomel electrode each for the reduction of Q plus to copper. Similarly, minus 0.45 is for lead. So from these two half wave potential and potential, we are able to determine the lead and copper in carbon steel, that is in percentage. So we have two halfway potential for two trace metals. Other industrial determination for trace metals are like we will able to determine the minor constituent of trace metals like copper, nickel, cobalt, manganese, chromium, molybdenum, tungsten, vanadium, titanium, tin, lead, aluminium in steel and ferroalloy of minor constituents. And we are also able to analyze copper based alloys like lead, tin, nickel, and zinc. Analysis of high purity zinc and zinc alloy, copper, lead, cadmium, tin, manganese, aluminum. Analysis of ferrous sulfate, zinc, lead, copper. Analysis of aluminum alloy, the analysis we have zinc, lead, copper, nickel, iron, and manganese. In pure aluminum, copper, cadmium, nickel, zinc, iron, lead. Then manganese. These are the ions or trace metals which can be determined by using polarography. Then we have determination of ascorbic acid, that is vitamin C. This is the ascorbic acid. Then we have a pentagon here, contain one oxygen and four carbon, and at the two position there will be carbonyl double bond O, and 3 and 4 position we have two hydroxy groups with one double bond, and then followed by some conjugation, and we have hydroxyl group are here. Then when it is reduced, that is it is oxidized, that is loss of electron. Then what happened? These H plus 2 H plus are removed, so it becomes a double bond O. We have dihydroascorbic acid. So this is determination of ascorbic acid in citrus juice by the standard addition and calibration curve method. So we have two methods, that is standard addition method and calibration curve method. So first one, calibration curve method. What are the preparation or procedure? They usually freshly prepared diluted juicy juice, that is citrus juice. Then we have to prepare a fresh stock of 50 milliliter of 0.2% ascorbic acid prepared. Just wait. Yes. So this is a 0.2% ascorbic acid, and prepare 5 standard solution of ascorbic acid in volumetric flask of 25 milliliter. To each one, add zero point 0.5 milliliter of 0.5 molar acetate buffer and different volumes of ascorbic acid. Then dilute the mark with diluted water. For each solution, record polarigram over the potential is minus 150 to 200 millivolt, versus here the reference electrode uses silver chloride in supporting electrolyte 1 molar KCl as the reference electrode. Then we have to plot the diffusion current versus concentration of ascorbic acid in calibration plot. Then we will able to calculate or determine the percentage of ascorbic acid present. Then the second part will be the standard addition method. Then squeeze an orange, grapefruit or lemon until about 10 milliliter of juice is obtained. Filter the juice through a porous funnel. Prepare 4 25 ml volumetric flasks. Add to each zero point 0.5 milliliter of 0.5 molar acetate buffer, 2 milliliter of juice, and standard addition of 200, 400, 600 microliter of 0.02% ascorbic acid. Dilute to mark the dilute water. Record the polarigram under the same condition as in the calibration step. Draw the standard addition plot and determine the concentration of ascorbic acid. Report the concentration of ascorbic acid, that vitamin C in original sample in moles per liter, and also impact. So here the standard addition is happening. What is the standard addition? It is the addition of 0.2% standard ascorbic acid, which is not there in the first step. In the first step, simply we prepare the juice, and we have four different flasks, and we have added zero point 0.5 milliliter of 0.5 molar acetate buffer. Okay. Then here what happened, and also different volumes of 0.2 ascorbic acid is there, but here what happened? 2 milliliter of, yeah, it is addition of 0.2% ascorbic acid, that is the standard ascorbic acid. So by the differential approach, we may determine the percentage of ascorbic acid in the sample. Then at the end, we have application of voltammetry. This is just a homologous to your polarography. So all these techniques can be applied quantitatively for the analysis of large variety of samples. The choice of a particular technique will depend on the analyte characteristic, expected concentration or other constituents present, and location of the sample. So these are the theoretical part. Then voltammetry instrumentation we have already discussed yesterday. Let's have a revision. This is the signal source, and we have the three electrodes here. One is the reference electrode, one is the working electrode, and one is the counter electrode. In working electrode, role is just the reduction, and it acts as the cathode. The counter electrode is the anode, where oxidation is supposed to be happen, and the role of reference electrode is to maintain the potential, constant potential. Then we will record the current to voltage converter here, which will convert the generated current to voltage, and we have the computer section here. So normal three electrodes polarograph. This is three electrode here. Linear scan voltage LSB generated to give different type of signal. The polarographic cell is made up of three electrode, that is working electrode, reference electrode, and counter electrode. And the working electrode usually micro electrode, whose potential is very linearly with time, because here the reduction is happen, that is the or treated as the cathode. The reference electrode is generally a saturated calomel electrode, that is SCE, or silver chloride electrode. Then the counter electrode, it is generally the platinum wire, or a pool of mercury that simply serve as the conduct, serve as to conduct electricity, or it acts as the anode. The potentiometer are allowed to impose the potential scanning between working and reference electrode, while the current flowing through the circuit is recorded between the working and auxiliary electrode, that is the anode, that is counter electrode. The computer cyclic voltammetry and trace analyzer from Metrom Limited can be used as an integrated instrument. So this is the advanced version of your voltammetry. It is to send the scanning parameter to the potentiostatic analyzer and check its correctness and handle the current potential output data. Then the what are the practical steps? There is sample treatment first in voltammetry. For this analysis, the sample must be in a solution form. Then we have addition of supporting electrolyte, that it is generally potassium nitrate, and which is 10 times the concentration of the analyte. This is very important. This is at least 10 times. Okay. Then we have a bubbling the for inert atmosphere. We use the nitrogen gas. So nitrogen gas should be bubble in the solution. Then the cleaning of electrode is happen. Addition of standard analyte. Scanning or registration of voltammogram. Measurement of peak height. Drawing the graph, calculation of the unknown concentration. So these are the fundamental steps for the practical involved in practical method of voltammetry. Then we have application of cyclic voltammetry. So this is coupled chemical reaction. We have cyclic means here the nitrate change to NaOH by with the reduction. Then RNaOH change to RNO, nitroso. Then again RNO accept electron with acceptance of 2H plus ion will give RNHOH. So to assist in proving the diagnosis, authentic sample of the hydroxylamine and nitroso derivative can be used to confirm. So uh, this is the hydroquinone, or uh, this is thyronine. Okay, so this is thyronine is an ether which may have convenient to be thought for of as representing the combination of the amino acid tyrosine and hydroquinone. So this is the uh, amino acid tyrosine, and this is the hydroquinone, that is benzene ring or phenyl ring. It contains two OH group. This is OH and OH in para position. This will be the hydroquinone. Okay. Then we have some addition of your tyrosine. Then we will get thyronine. So this is a compound, a ether of thyronine, And if we go for voltammetry analysis of this compound, we have current versus potential curve here in silver chloride reference electrode. We will get a graph is just like this. That means this graph is shows this is just a cyclic type, and the cyclovoltammogram of 3.3 milligram per 25 milliliter uh, chloramphenicol in zero point 0.1 molar acetate buffer, pH 4.62, carbon paste electrode. So this is the compound of like the initial two electron oxidation generates proton and organic content, which is readily hydrolyzed to benzoquinone and trityrene. So this is not hydroquinone. This is now it is benzoquinone. Benzoquinone with tyrosine, we will get this one, and this then by loss of H plus and we will get this, and by what are that by byproducts? This is the benzoquinone, and this will be the tyrosine. Amino acid, that means it contain amine and acid. This becomes amino acid. Amino acid means what? It contain amine group and acid group. So this is amino acid and this is benzophenol. Then we have the amino acid again lose one electron to give this compound, right? So this becomes double bond O, carbonyl, and H is here. Then for these three compounds A, B, C, and D, we have cyclic voltammetry just like this. So these are the change in current with potential. So when this type of changes occur by loss of electron, we have this type of graphs are obtained. Then again the benzoquinone added by two electron, that will be the hydroquinone. This is peak C. This is the peak C, where the current is very high with the potential. Then this is the peak D. Again hydroquinone changed to benzoquinone, peak D. Again the current decreases. So these are the some applications of your polarography, followed by amperometry, and the last one is the voltammetry. So this is a very easy unit for remembrance, and you have to remember some of the things. Okay, and then at 6:04 p.m. today, Chandrayaan 3 will land at moon surface. So I missed that one. So let's have the live video for few minutes, and after that we will switch on to our discussion. So are you listening, students?
Yes, sir.
Okay,
Yes,
okay,
sir.
okay. Thank you. So let's have the landing of Chandrayaan 3 on moon surface. So congratulations to all of you that Chandrayaan 3 successfully landed on the moon surface. And thank you, congratulations to you all. And I we just missed that moment, so that's why I switch over to that part. So now we are the third country in the world who third or fourth, I think, after America, Russia, and China. I think we are the fourth country in the world to have arrival at the surface of the moon. So congratulations to Team India, Team ISRO. And so students, let's have 3 to 5 minutes break. So after that, we will have discussion on experimental techniques in thermal analysis or thermogravimetry. So till then, let's have some refreshment, or then at exactly 6:24, we will have the second part of today's session. Okay, thank you. So welcome back, students. And in the second part of today's class, we will have Unit 10. That is all about your thermogravimetric analysis, which is in short, it is TGA, that is thermogravimetric analysis. And this is Unit 10. And this is a very popular and widely used technique in research field. And in this technique, what happened? Now, if sample is mm, applied to a heating chamber, and with rise in temperature, what happened? There is decomposition, or there is disintegration of that compound is supposed to be happen. That some byproducts or some part of that compound will left, and we will have small compounds as the product. So these small compounds will have different mass as compared to the original compound. So these things are very much catch by the thermogravimetric technique. So I have prepared one PPT for you. This is this include unit 10 and 11 both, and tomorrow we will have unit 11, that is differential scanning, calorimetry and differential thermogravimetry, also one part is there. So let's have the first one, thermodynamic analysis, thermogravimetric analysis. So, as the name suggests, thermo means it is heat or temperature, and gravimetry means it is determination by weight. It is known as gravimetry because every chemical analysis or any chemical experiment, it is broadly of two types, that is gravimetric analysis and volumetric analysis. If the analysis is done by weight, it is not gravimetry, and if it's done by volume, it is called volumetry. Then this is the thermogravimetric instrument or machine. This is just the highly advanced TGA, and this is just the empirical figure where the heater is here. That means it is the heating chamber, and this is a sample holder where we put the sample, and this is a measuring system which will measure how much sample will disintegrate or how much sample is decomposed, and what mass is left and what mass is left out. The differential mass will be measured by this system. This is measuring system. So we have mainly of three important or main component of this instrument, that is the heating chamber, sample holder and the measuring system. And this is the, and here this is the sample holder. Okay, and this is the heating chamber, and this is the your measuring system, how much sample is disintegrated or decomposed. Then we have TGA, that is thermogrammetric analysis by mass. Then differential TGA, in our next part, unit 11, we have temperature difference. If we have a mixture of compound, then this DTA will have application. Then differential scaling calorimetry, this is in our latter part. Then we have just general confirmation where the sample is here, that is a component, and we have the furnace temperature programming here, or we may use the thermobalance. This is just the absurd now it is not used because advanced techniques are already brought up. So that's why thermobalance is one of the main component in thermogravimetry in previous time or past time, but in current situation advanced machines are used. Then at the end we have the data. The physical property, this is the physical property measurement. This is measurement by mass. This is a sensor is there. A controlled atmosphere is maintained here by a that is noble argon gas or nitrogen gas environment. Then a temperature programmer will be there. The temperature programmer means which can control the temperature for a particular compound, and all interfaced to a computer. That is at the end, all will connected to a computer. This dynamic TGA, that means temperature will vary. This isothermal TGA, that means at constant temperature. We have two types. When the temperature changes, it is dynamic. When the temperature is remain constant for a particular compound, then this is known as isothermal. The measure changes in weight. This TGA measures changes in weight with relation to change in temperature. The measured weight loss curve gives information on. There will be a curve like this. A curve is like this, just a step like curve. That is one step to another. When byproducts are removed, then the mass will decrease. So the curve is like steps. We will have the curve. Changes in sample composition. This will be the one reason for mass loss. Or the second one is the thermal stability information, kinetic parameter of chemical reaction. And what TCA can tell you? It can tell you the thermal stability of the material. That is how much temperature or how much heat the material can sustain. Well, this analysis can tell us. That is explicate decomposition mechanism, fingerprint material for identification and quality control. And oxidative stability of the material is also there. That is in presence of oxygen, this compound may oxidized or decomposed, or thermal decomposition will occur at inert atmosphere. This thing can be studied. Composition of multi-component system. Multi-component system means it is just like a mixture. When I mixed calcium carbonate with magnesium oxide, let us, then we have a two component mixture, and this different component or multi-component system can be analyzed uh, by its composition. Then we have estimated lifetime of a product. So how much is the lifetime, and that is at related to thermal stability. At what temperature, what is the lifetime of that material. Then the kinetic decomposition, effect of reactive or corrosive atmosphere of material, moisture and volatile content of the material. Loss of moisture, drying, desorption, these things happen when there is a loss of moisture, means it is removal of water. That means mass loss will be 18 unit. Then drying, if some drying agents or drying groups are there, like alcoholic group, ether group, then this will be loss. So there will be mass loss. And followed by desorption, if it is adsorbed on a surface and we applied the heat or temperature, then what happened? There will be desorption. They will detached from the surface of the adsorbent. So mechanism, the weight loss, the first one is the decomposition. Then we have it is a breaking of chemical bonds. Then evaporation, loss of water or loss of volatile and elevated temperature. Then there probably the reduction may happen. That is a loss of hydrogen or ammonia may happen as gases. And the last thing will be the desorption. That is reverse of your adsorption. Then how the weight gain may happen in TCA. Weight gain may happen by the addition of oxygen, that is oxidation, or by absorption or adsorption. So these two phenomena, if happen in a particular material, then weight gain may happen. And this weight gain concept is very much exception, or very few compound shows weight gain in TGA. So all of these are kinetic processes. They are related to the rate. Then we have this is the thermobalance. This is the thermobalance, and this is the null point, like the balance used in our old time when we purchase rice dal. Then the shopkeeper will hold one balance in his left hand, and then the balance of two pans. One side there will be weight of 1 kg, half kg, 2 kg, and at the right hand side we have the things to purchase. That is, it may be rice dal, anything else. So in the similar way, it is just a balance, that is the thermobalance, and it is a null point or the balancing point, like the shopkeeper has in his left thumb. When he when he lift the balance, then the null point will goes right or left depending on the weight of the either pen, left or pen or right pen. Similarly, here what happen, there is a null point here, the null sensor will be here, and this balance operate on a principle of null balance. At a zero or null position, equal amount of light shine on the two photodiodes. So when the null balance or null point is zero, that means it is in balance. When the compound is placed here, if the balance move out of the non-position, an unequal amount of light shine on the second photodiode, current is then applied to the meter movement to return the balance of the null position. The amount of current applied is proportional to weight loss of the gap. So it is just like when the temperature is applied, and here what happened at the extreme end, at the right hand side, two photodiodes are here which control the current. So when the weight loss of the compound is happen, then the current will fluctuate. So this will indicate that some weight is loss in the thermobalance by application of heat. So this is again the thermobalance. So here, this is the coil, this is the heat chamber, right? This is the heat chamber, this is the lamp, and this is the sample holder. These are the photo cells, this is the shutter, and through this we have two pans here. Okay, balance pans here, and when we put the sample, then if weight loss is there, then this will be indicated through this through by the change in current. This is the plot of TGA. This is a sample plot. Just see here. This is the plot of temperature versus weight. With rise in temperature, how much weight is lost, right? So this is the curve. Just see here. Here mass is 100. So from 100, it is with rise in temperature, the mass is lost like this. So mass is lost. Again here what happened? This becomes saturated with a rising temperature. So we have to extrapolate, that is in y-axis and x-axis. Then we have the temperature of 537.67 for our fast degradation. This is the fast degradation. Then we have the the second one is here. The second one is here. This will be the second one, that is completion of the reaction as 587 degrees centigrade. So by this type we can analyze the TGA plot. Then classification of TGA plot, these are the type of TGA plot we may have for our compound which is to be analyzed. If it is a straight line, then no mass loss will be there. If it is just a half slope here, then desorption or drying or mass loss is large followed by mass plateau. So this is just a desorption or drying. So if this type of curve you get, then this is single stage decomposition, just one stage decomposition. If it is just a D like, it is multi-step decomposition. If it is E type, then it is similar to D, but either due to faster heating rate or due to no intermediate. So if the heating rate is faster or no intermediates are formed, then we may have this type of plot. Then if I have this type of plot like F type, then atmospheric reaction will be there and increase in mass due to oxidation. Here, just see the mass increase. So this is due to oxidation or absorption or adsorption, or this may be due to some atmospheric reaction. Then at the end we have G type. If G type, it is similar to F, but product decomposes at higher temperature. If it is like this, so initially the mass increases, then this is due to oxidation, absorption or desorption, or some atmospheric reaction may happen. And after that this will be remain parallel to the temperature axis. That's why it is indicates the completion of this reaction. Let's have an example. If calcium oxalate is decomposed, what What is the formula of calcium oxalate? It is calcium oxalate monohydrate. So this is CaC2O4. What is oxalate? It is from oxalic acid. What is oxalic acid? It is just two unit of COOH. If two unit of COOH is bonded through carbon, it is known as oxalic acid. And from oxalic acid, if I remove the two hydrogen, it becomes oxalate ion. So that means C2O4, 2 minus is the oxalate ion. So this is calcium oxalate, CaC2O4 monohydrate means dot H2O. So in the first step, what happen if I put some or apply some heat or temperature that is nearly 100 degrees centigrade? This water will remove first. So this is the first step. Water will remove and the mass will be lost. Decrease in mass will be there. So this will be the calcium oxalate. Then the second step, calcium oxalate again at a particular temperature change to calcium carbonate and carbon monoxide gas will liberate. Then after that, from calcium carbonate, again carbon dioxide will liberate. So at the end, we have calcium oxide. That means from calcium oxalate monohydrate, we have calcium oxide as the end product. That means this conversion from calcium oxalate monohydrate to calcium oxide, we have two phase intermediate. One is the calcium oxalate phase and second one is the calcium carbonate phase. So the plot will be like this. So just see here, this is from 100, the mass is just remains same. This is the first, that is loss of water. Then this remain constant. This is again loss of carbon monoxide. This is again loss of carbon dioxide, and this will go on. That means the plot will be like this. The first curve is for the loss of water. Second curve is due to loss of carbon monoxide. Third curve is due to loss of carbon dioxide. Then these are the temperatures at which these decompositions happen. So this type of curve you will get for calcium oxalate monohydrate. Then these are the common thermodegradation profile of some common polymers like polyvinyl chloride, polymethyl methyl acrylate. Then this is PTFE, that is and this is pi. So these are some polymers which TGA graph is here, and this the mass is just down here for PVC. Then it is a two phase decomposition, then it remains parallel. This is just like this. That means there will be one phase degradation. Then similarly, these things are happen. Then at inert atmosphere is maintained, where polymerization or carbonization occur. Air atmosphere, oxygen in air active ingredient in degradation. Then TGA curve, not fingerprint curve. Fingerprint means it is just like human beings. So every human being has a unique fingerprint. So like this, every compound has a unique fingerprint TGA curve, which cannot be which is cannot be same or equal as any other compound. So this is known as the fingerprint curve. So like in our infrared spectroscopy, IR spectroscopy, there is also a fingerprint region is there. That means for a particular compound, the IR absorption is unique for that particular compound, and this will be not equal or same to other compound. This is known as fingerprint curve. So for a particular compound, TGA curves are not fingerprint curves. That means more than one compound may have the same TGA curve, because most events that occur in TGA are kinetic in nature, meaning they are dependent on absolute temperature and time. Any experimental parameter that can affect the reaction rate will change the shape, transition temperature of the curve. So these things include pan material, that is in a thermo balance, or this is the sample holder, also known as the pan material. Pan material may be alumina pan, which can resist up to 1700 degrees centigrade, or it can be platinum band, which is very much costly, but it is a good thermal conductivity, but not always inert due to its catalytic activity. So then ramp rate, suitable heating rate to detect overlapping reaction. Then purge gas, that is the inert gas purge, that is the pressure of the gas. This is protective gas for valence, purge gas or reactive gas for the furnace. Then sample mass, if it is low mass, resolution limit of microvalence. If it is high mass, pronounced thermal gradient. Then we have effect of heat rate, that is 10 milligram sample of PTFE heated at 2.5, 5, 10 and 20 degrees centigrade per minute. This is the time with temperature and mass. We have the plots like this. And the slow heating approaching thermal equilibrium, if it is fast heating, generates thermal lag. So this is the observation when the heating is fast or heating is slow. Then we have shift in onset with heating rate. So this is the final temperature, this is the initial temperature, this is the heating. Then we have the plots like this for the same PTFE compound. Then we have the temperatures like here. It is the temperature for the fast decomposition followed by this one. Then these are some examples. Then effect of sample weight. If the sample weight is more, then maybe the temperature becomes the fast decomposition temperature may be more. So like this, for the green color, this one 418.3 degrees centigrade, and this is for your 414.5 degree centigrade. Third one is for 413, and fourth one is for your 407. That means when the mass of the or weight of the sample is decreased, here it is written, when polystyrene is 2.7 milligram, the fast decomposition it has 407.6 degree. When it is 5.4, that means double, it is 413. If it is again double, 10.2, it is 414. If it is 17.6, it is 418. That means gradually when the weight of the sample is increased, the fast decomposition temperature is also increased. The effect of purge gas here, that is calcium oxalate decomposition as a function of atmospheric carbon monoxide oxidizes in the presence of oxygen. So this is differential scanning calorimetry with a TGA curve, which we will discuss in the next session. And we have the TGA curve here. That is for your calcium oxalate monohydrate. This is the loss of water, loss of carbon monoxide, loss of carbon dioxide here. Then we have differential in the next part. So let's have the PDF first. So this is the plot in your IGNO PDF, and the change in temperature or the temperature used, it is the final temperature minus initial temperature. Okay. So this is the instrumentation. This is the thermobalance. We have the sample holder here. This is the furnace or the coil. The 3D diagram is also here, which I have already shown to you. This one. So, yeah. Okay. Yes, this one. This is the coil. This is the sample holder. Okay. So this is sample holder. This is the coil or the furnace. This is the atmospheric control. This is the programmer. This is the sensor is already here, that which will indicate the temperature. Then it is the recording balance and the balance control here. So these are the instrumentation for your thermobalance. So there will be a null type balance, there will be deflection type balance, then furnace we may use from minus 150 degrees centigrade to 2000 degrees centigrade. Temperature measurement and control, we have a sensor which would control the temperature through your chromal alumel thermocouple is there for heating purpose. This thermocouple will maintain the heat or have the heating capacity of up to 1750 degrees centigrade if it is made up of platinum and 10% rhodium. Then there is a recorder which can record the datas. Then we have the furnace and sample assembly diagram here. Okay, then I just read out this is a reference balance pan. This is flow meter, gas in, flange, glass body, flow meter, water in, water out, and this is a sample container or holder, and this is the furnace assembly. Okay, so when gases are liberated as byproduct, and then these gases maybe trace out to sensor. Then we have thermodynamic curves are here. This just like these curves may be obtained. Then we have what are the error maybe the error in TGA we have buoyancy effect. This may be the one error that is due to the moisture atmosphere or the sample holder. Generally, it is the crucible, inert crucible made up of porcelain. Uh, this may contain some volatile material or some moisture, and if we take the sample in a crucible, what happen the crucible is wet, before wet and after wet is recorded, and the difference will be the weight of the sample. So that's why if the crucible contains some volatile substance as impurity or some moisture, then it may be an error, an effective error for your TGA. Then condensation of balance suspension. When the balance suspension is condensed, then we also have some error. Then we have a random fluctuation of balance mechanism, a reaction between sample and container, convection effect from balance, then turbulence effect from gas flow, induction effect from furnace. Then error 3 type, that is random fluctuation of balance mechanism, can be avoided by proper placing of balance in the lab, and so there will be no fluctuation if the balance is placed at a proper place in our lab. That means it should have a strong base which may not be tilted in either way or either side. Then the point 5 convection effect from the furnace. This error can be avoided by sensible choice of sample container. Okay, the last three error have to be considered in the design of the furnace, that is turbulence effect of the gas flow and induction effect from the furnace. This is the manufacture error which can be sought out at their manufacture level. By avoiding the excess heating rate and proper gas flow, the rate of some of the mentioned error may be avoided. So these are the two very common error occur in TGA, that is excess heating rate, that is it should not be fast heating, it should be moderate heating or slow heating. And then the gas, the purge gas or the proper gas flow rate will be there. Then calibration of thermobalance for the measurement of mass, it can be done by adding known mass of sample container and noting the reading of the chat. Temperature calibration, ferromagnetic standard are used for this purpose. In a magnetic field, their substance on detectable mass change. The ferromagnetic standards are quite suitable for the temperature range from 242 to 771 degree centigrade. So these are the standard used. So how we can interpret the TGA curve? Let's have a conversion, that is calcium carbonate solid is decomposed to calcium oxide and carbon dioxide. So if I calculate the molecular mass or molar mass, then calcium carbonate will have 100 gram and calcium oxide will have 56 gram, and carbon dioxide will have 44 gram. So if carbon dioxide gas is gets separated from calcium carbonate, we have percentage of mass loss will be, it is 44 by 100 into 100, it will be 44%. Then this will be the, this will be the plot of your TGA, that is, it is indicated by the dotted lines. So here mass loss will be there. So this is the carbon dioxide decomposition. Okay, and the reverse one, this one, which are just downward curves. These curves are DTG, that is differential thermogravimetry, which we will discuss tomorrow. Okay, and this is about your uh, and for DTG, that is differential thermogravimetry, the y-axis has thermogravimetry percentage, because this is differential versus the temperature. Okay, then we have this is already discussed, and also I find I try to recall this one, PTFF, polytetrafluoroethylene, PTFE. Okay, so we have the TGA for some polymers here. This is polyvinyl chloride, and this is polymethyl methacrylate. LDP is low density polyethylene. This is your polytetrafluoroethylene, and the last one is the polystyrene. So if the weight or mass of the substance taken is same, but the TGA curves are different. Okay, so this will be the thing. Then what are the factor affecting? The factor affecting are furnace heating rate. This may be high speed or slow speed, recording or chat speed. This is another factor. Then we have furnace atmosphere. It should not be the general atmosphere, it should be an inert atmosphere. Then geometry of sample holder, location of sensor is a vital factor. That is sample holder geometry is what it is, whether it is square, it is circular, it is rectangular, or what type it is. Then on the basis of that, there will be but the heating must be controlled. Then location of the sensor is another important part. Sensitivity of recording mechanism, composition of sample container. These are the important things. Then what are the sample characteristics or the factors? The amount of sample taken. Then solubility of the sample with evolved gas in sample. That if let us calcium carbonate liberate calcium dioxide gas, and if calcium dioxide if calcium carbonate is soluble in carbon dioxide, then there will be an error. So this must be a must be one thing we should remember, or we should have in our mind, that the gas evolved should not be soluble with the sample. That is, carbon dioxide must not be soluble with calcium carbonate. And the particle size, heat of the reaction, sample packing is also an important factor. That is, it is cubic close packing or hexagonal close packing, or what type of geometry it has. It is monoclinic, triclinic, or something like that. Then we have uh, sample packaging. Then after the nature of the sample, then thermal conductivity. So this includes your sample characteristics. Then we have furnace heating rate. That is, the heating rate is fast or slow. We have three relations for a single endothermic reaction. Endothermic reaction where heat or temperature is absorbed. This is known as endothermic, or gain of heat. And if it is loss of heat, this will be exothermic. So thermogrametric analysis, all are endothermic. So that means final is greater than initial, right? TIF is greater than TIS. That means initial temperature rate is faster than initial temperature rate is slower. So that means F greater than S, and it is the final temperature. This is faster rate and slower rate, and the differential. Then we have three equations here. Then recording of chat speed. The chat speed on the recording of the TG curve of rapid or slow reaction has pronounced effect on the shape of TG curve. For a slow decomposition, the reaction low chat speed is recommended for recording the TG curve because at high chat speed, the curve will be flattened. If for a compound the decomposition is slow, in that case we have to apply slow heat. Okay, and if we apply high heat, then at high chat speed what happen, the curve will be flattened, there will be no curvature. So for a slow reaction followed by a rapid one at the lower chat speed, the curve will less separation in the two steps. So this has to be uh, remembered. Okay, furnace atmosphere is another important factor. The effect of atmosphere on TG curve, it has the type of the reaction, nature of the decomposition product, type of atmosphere employed. These things are there, and always the dry oxygen or dry nitrogen atmosphere is maintained. Then we have the same example here, calcium oxalate, monohydrate. These things also already discussed, and they depend on the particle size, the surface area, lattice effect. These are the factors on which this decomposition matters. Sample holder size already discussed. Then effect of sample mass. That is, this is effect of sample mass. This is effect of sample mass. This one. Yes, this one. When the sample mass or weight of the sample increases, the decomposition temperature also increases. This is for polystyrene example. Then effect of sample particle size. If the size is larger, then decomposition will be at higher temperature. The particle size will cause a change in diffusion of the evolved gas, which will alter the reaction rate and hence the curve shape. Smaller the particle, greater is the extent of decomposition at any given temperature. The use of large crystal may result in apparent very rapid mass loss during heating. This may be due to mechanical loss of part of the sample by forcibly ejection from the sample container, and these things are there. So just remember, when the size is sample size or particle size is larger, the decomposition will be at higher temperature. That means it has slow decomposition rate, and if it is smaller size, the decomposition will be at faster rate. Effect of heat of reaction. This is very important. For a particular compound, the heat of reaction is constant. That is, heat of reaction will affect the extent to which sample temperature proceed or succeed the furnace temperature. This depends on whether the reaction is exothermic, endothermic, or consequently the extent of decomposition will also be affected. So this also depend on the heat of reaction. The other sample characteristics are sample packing, nature of the sample, thermal conductivity. These are the other factors. Then application. Then in application part, we will able to determine the purity and thermal stability of the sample, solid state reaction, decomposition of inorganic organic compound, determining composition of the mixture, corrosion of metal in various atmosphere, pyrolysis of coal, petroleum and wood, roasting and calcination of minerals, reaction kinetic studies, evaluation of gravimetric precipitates, oxidative and reductive stability, determining moisture, volatile and ash content, then dissolution, sublimation, vaporization, sorption, desorption, chemisorption. So these things, all these things can be well understood by using TCA of any compound. Then in the end of this unit, we have analysis of some inorganic organic compound. Then if it is a binary mixture, let's we have a two mixture AB plus CD. Then at the initial state, the mass of the compound will be at the higher side. That means it is the first compound to be separate. So what happen? There will be separation will be like this. That means here there is a loss of two unit, and this is also loss of two unit. That means by combining these two, we have this one AB plus CD. We have the net plot will be like this. This is thermodynamic gravimetric curve of two compound AB and CD and their mixture. This is the separate when A, B, and CD are separately undergo TGA, and this is the mixture when AB plus CD undergoes TGA. Okay, then we have the loss of X milligram from B to C and loss of Y milligram from C to G. So these things are there, and we have analysis of this is one example when magnesium carbonate and calcium carbonate get mixed. Then we have this is the TG curve of mixture of calcium and magnesium carbonate. Then we have the curve. This is one, two, three. So three units are removed. What are the three units? This is magnesium oxide, calcium oxide, and carbon dioxide is in common. So that means three units are here. So the fast decomposition may be due to calcium oxide. This is the first thing which may be decomposed out, then followed by magnesium oxide and calcium oxide. Then here the temperature is also maintained. I mentioned here it is yes, M1 to M2. This is M1 to M2. M1 to sorry. The M1 to M2 is the loss of carbon dioxide. That means here carbon dioxide is lost. Okay, at 500 degrees centigrade and 900 degrees centigrade due to decomposition of calcium carbonate. And here it is 500, it is 900. So here carbon dioxide is lost because calcium carbonate decomposed at higher temperature. Then we have the mass of calcium oxide here. The mass of calcium oxide, that is M3. Okay, so this is M3. It is equal to 1.27 into M1 minus M2. So this will be the equation. Again, this is the same reaction 100, 56, and 44. Then 1 mole of calcium carbonate contain 1 mole of carbon dioxide. So M1 minus M2 mole of calcium carbonate contain M1 minus M2 by mass of carbon dioxide. Here it is equal to mole of calcium oxide. So by stoichiometry we have final, that is M3 equal to 1.27 M1 M2 gram. M4 is just like this. Just go through this mathematical derivations. Okay, these are just stoichiometric things. That is only the comparison, that how much weight is lost with respect to what, this much. Here calcium and calcium oxide, here it is a comparison. Here magnesium and magnesium oxide. So just go through these things. Then this is the second example, calcium and magnesium oxalate. The same principle is goes on here. Then calcium oxalate monohydrate, the fast degradation is at minus 135 to 220 degrees centigrade. Then followed by the second one, conversion to calcium carbonate and carbon monoxide at 400 to 480. Then calcium oxide carbon dioxide is this one. Then this magnesium oxalate at 135 to this and this. The curve is just like this, mixture curve. This is the DTG percentage. Okay. Then the another silver nitrate with copper nitrate. The curve is like this. These are the temperature, and we have a complex mixture also, that is with the DTA or with complexing agents, and here it is strontium carbonate is here. Then we have mixture of calcium, strontium, barium. All the three compounds are mixed. Then amount is determined by following this equation. Then organic mixtures are also here, like vinyl acetate, copolymer, and this is the TGA graph, and this is the 23% mass loss. It is calculated. Then precipitation reaction, we have beryllium with NH4 whole twice HPO4, that is ammonium hypophosphate. It will change to beryllium ammonium phosphate dot hexahydrate, and the TGA plot will be at 900. Just read these things, okay? Analysis of polymeric material, the remain chain scission, side chain scission, elimination, depolymerization, cyclization, cross-linking. Reaction kinetic also can be studied through TGA by using Arrhenius equation, that is K equal to A e to the power minus EA by RT, where K is the equilibrium constant and A is the Arrhenius constant, where EA is the activation energy, R is the universal gas constant, and T is the temperature in Kelvin, where K is the rate constant. Okay, so this is the decomposition, that is alpha d alpha by dt, where alpha is the fraction of reacted decomposed decomposition coefficient with respect to temperature, let's say with respect to time, that is 10 second. We have k alpha to the power m 1 minus alpha to the power n. These things just, then at the end we have this complicated table related to kinetic analysis, and these are the notation: degradation 1, 2, 3, 4. Then we have A2, A3, A4, B1. These are the notations, and these are the integral equation of the rate constant, and these are the differential equation of the rate constant. So just try to remember only one dimension and two dimension and nothing more than that. Okay, just try to remember these two equations only, and this will be the end of your unit 9 and 10 today. It is application of polarography, amperometric titration with voltammetry, as well as the second part, that is your thermogravimetric analysis. And if and today we have cover up to unit 10, and tomorrow we will have unit 11, that is differential TGA, scanning calorimetry and thermometric titration. Then we have the last part, unit 12, radioactivity. Very interesting this one, radioactive and nuclear chemistry. And after that we have the last unit, that is radio analytical methods. And in this part we will have radio tracer, then isotope dilution analysis, then we have a soft stoichiometric isotope dilution analysis, activation analysis. These are related to radiology or radio analytical methods. Okay, so we will have 2 days left, that is tomorrow and day after tomorrow, and after that you will we will complete all the unit paper of your PGDSC program, as the 3 papers are already completed. So we are just T unit left to complete this paper. And if any question or anything anyone to say or ask, over to you students, and if not we may wind up the session. Okay. So do not waste time. So every day you should study little things that we have discussed in our daily class. So you have to make your own note for your theory examination, and regarding your practical, again I will uh, say you that you should check your email frequently. So you may have some mails from IGNO Center Bhubaneswar regarding your practical classes and practical examination related things. And yeah, I hope we have practical classes in the month of September, maybe. Okay, maybe in the month of September, and before December we will have the practical examination also. So in December you have the in December you have the practice. In December you have the that one theory paper examination. Okay, so best wishes to all. So thank you from my side, and thank you from Regional Center Bhubaneswar, IGNO Regional Center, for your kind cooperation and patience hearing. So thank you to all.